Hello everyone, my name is Rose Sanchez and today we will be presenting how to use programmable devices to calculate and simulate cosmological redshift effect. And my team members are
Juan Rivera Santiago,
Kevin Montalvo Vega,
Jose Quiñones,
Kevin Ramirez Martinez.
And this is our project.
The objectives for this project are: learn programming and interfacing programmable electronic devices, design the interface to be used with LEDs, create a prototype that demonstrates the redshift effect according to speed and direction of the object.
In this timeline, we can see the predicted time frame for each of the deliverables throughout the lifespan of this project. And it includes the current phase we're in, and it shows that we're currently in sync with our planned schedule.
Metrics for success. Program a microcontroller to interact with LEDs. Individually address LEDs in a sequential form. Control timing sequence and color of LEDs according to user-selected parameters. Able to explain in a visual manner the redshift effect and the cosmological redshift effect. Demonstrate the effect of an object that moves towards and away from Earth at a variable speed.
When students begin learning concepts regarding physics and wave properties, it is common for there to be difficulty grasping ideas that are abstract or not visible in the daily life. One of these notions is the redshift effect. The solution is to help them visualize it with a physical demonstration. The current approach is to design an interactive prototype which will allow the students to visualize the redshift effect from inputs provided through buttons. Said tool should have the capability of being reprogrammable or modified for tasks added in the future.
The redshift effect is seen in electromagnetic waves detected from a moving source which speeds further away from the sensor. When the distance between source and listener changes, the frequency of the wave is altered in a similar manner seen in mechanical waves. When in outer space, we can observe this effect on sufficiently far away light sources, such as stars, planets, and cosmic dust. To the right, we can see some very important equations, particularly the Hubble law, which can be used to calculate the recessional velocity of the galaxy as long as we are far enough away that we have passed the Virgo cluster. Here we can see that it depends on a Hubble constant as well as the distance to the galaxy which we are approximating. These values are then used to approximate the value of a perceived wavelength, which is dependent on the wavelength at rest, the recessional velocity of the galaxy that we just calculated, and the speed of light. Now, what is the difference between redshift from the Doppler shift and cosmological redshift? In Doppler redshift, only the relative velocities of the emitting and receiving object matters, but in case of cosmological redshift, the emitted light also gets stretched out, thereby increasing its wavelength, by the expanding space as light is also in the space. We can say the velocity of an object in space is accompanied by the inherent expansion of the universe. The radiation travels through expanding space in cosmological redshift. The observation that all sufficiently distant light sources show redshift corresponding to their distance from Earth is known as Hubble's law. An interesting thing that should be of note here is that there could be objects who are incredibly far away, and because of the expansion of the universe, their speed could be seen as close to the speed of light, and therefore the human eye would be incapable of detecting them. In order to understand these, we move all the amplifications or reductions into an area within the visible spectrum.
In this block diagram, the basic outline followed for the assembly of the prototype is shown. As seen in the yellow block, the user will have 4 options to choose from, which will assign and feed parameters to the FPGA to calculate the corresponding wavelength shift with the object viewed moving towards or away from the viewer. Once this calculation is done, the appropriate delays of RGB values are fed to the LEDs, where the visualization takes place. As for power requirements, a 5-volt source will be fed to both the FPGA and the LEDs.
In the following video, we have the basic prototype of the function and the hardware setup for the LED layout.
Big thanks to the Industrial Affiliate Program and to all of our sponsors. If you have any questions, feel free to email us at any of the below emails.
Otherwise, feel free to use the link presented below to join us during the IAP Fall 2021 Virtual Conference.